Hi, my name is Bryce, and in this video we're going to be talking about common types of matrices encountered in a linear algebra course, at least up until the LDU factorization part of said course. So first let me show you here. This first matrix we have is a generic matrix. We'll be using this to demonstrate the properties of the other matrix. This generic matrix is just here to represent any arbitrary matrix that could be any arbitrary matrix that could be formed in a 3x3 fashion. This next one we have is the identity matrix. We call it the identity matrix because whenever we multiply this matrix by any other matrix on either the left or the right hand side, the result is the other matrix matrix exactly without any mutation. So let's witness this. We have this generic matrix, and then we have the identity matrix. We're going to go over here, and we're going to evaluate this. Notice how the result remains exactly the same. Let's try multiplying using. Let's try multiplying with the identity on the left side. Identity times the generic. Go over here, and we evaluate it, and it's still the exact same matrix that went in. So now let's talk about a permutation matrix. A permutation matrix looks exactly like an identity matrix, except some of the rows or columns have been swapped. Well, mainly some of the rows have been swapped. So in this case, row 0 and row 1 have been swapped. So if we multiply a permutation matrix times the arbitrary matrix, the row 0 and row 1 will be switched. Let's look at this. So we have the permutation matrix, P, times generic matrix. We go over here, and we're going to evaluate it. And the result is that row 0 and row 1 have been swapped. So the new matrix M equals generic matrix G, well, permutation matrix times generic matrix G. And row 1s and row 0 have been swapped. This is because row 0 and row 1 in the original permutation matrix have been swapped. So that's how a permutation matrix works. Now let's talk about elementary matrices. An elementary matrix is one with ones on the diagonal, and then a factor E in one of these three lower triangular spots. An elementary matrix is special because it can be used to by multiplying it to a matrix. It can perform the elementary row operation called a linear combination. This is the theoretical basis for the LDU factorization. Let's see its work in action. So we click on we're gonna multiply by E. Go to the generic matrix. Go over here. Go down and evaluate it. And so the result of this one was that for the generic matrix, we added E times row 0 to row 1. See? Because you have E times A, there's that A, plus D was in the original. Then you have B, so B times E plus E, so we subtract it. And then you have C times E plus F. Let's see what happens if we multiply using the generic matrix first, and then the elementary row, the elementary matrix. Let's go over here and evaluate. So if we do it the other way, then it appears to add the column. Well, the scalar E times column 1 to column 0. That form will probably not be used in your LDU factorization. But so we can chain these elementary matrices together to fully reduce any matrix that does not require a row exchange. Interesting property about the elementary matrix, let's select it right now, is that the inverse of it can be computed by merely negating the non-zero box. See, the inverse is equal to E. Let's invert it again. It's equal to negative E. E, negative E, E, negative E. And because we know that each of these elementary matrices has an inverse, and that we can multiply all of them by chain. This is one of the theoretical bases for why an LDU factorization proves that matrix is invertible. Another interesting thing to think about. Another interesting matrix would be let's identify this. It would be a diagonal matrix where you have non-zero elements only on the diagonal. This matrix, let's evaluate it. Diagonal matrix this matrix has the interesting property that any matrix that it's multiplied to will have each of the corresponding rows multiplied by the given scalar. So if this diagonal matrix were multiplied by another matrix, the first row of that matrix every element would be multiplied by A. The next row every element would be multiplied by B, and the next row every element would be multiplied by C. Let's try that. So we take the diagonal matrix and we go up here to the generic matrix. We have a little bit of clashing between them since we're reusing some symbols, but it should probably not be too confusing. Let's click evaluate. So as we can see, the original generic matrix had A, B, C, and each element of the 0th row has been multiplied by A. For the first row, D, E, F, every element has been multiplied by B. For the second row, G, H, I, every element has been multiplied by C. So as we hypothesized, or as we said would happen, the diagonal matrix multiplies each row by its corresponding scalar factor. Another interesting thing about diagonal matrices is that the inverse is equal to the multiplicative inverse of each of the diagonal elements. So if you ever need to invert a diagonal matrix, you can just put 1 on top of them and divide wherever it is by 1 to compute the multiplicative inverse. So say we had h over a, h over b, and h over c. The inverse would be a over h, b over h, c over h. You see how that works? So the inverse is just the multiplicative inverse. Some people call it the reciprocal. So, well, that's probably enough about different types of matrices. Thank you for listening. Have a good day.